Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very fortunate to be joined by Robert West, who's come down to us from JPL. And we thank the Outer Planets Colloquium series at JPL for making Rob's travel available to us today. Bob has achieved his BS in astronomy at Caltech and then did a PhD at University of Arizona. And he has spent a career where he's been interested in the radiative transfer of planetary atmospheres, especially in observations and interpretation of multiply scattered light as observed by spacecraft and ground instruments. He's been involved in a range of NASA missions, including the Solar Mesosphere Explorer, Galileo UVS, the PPS instrument on Voyager, and he was part of the team that observed the Shoemaker-Levy impact at Jupiter with Hubble Space Telescope. And Bob has also been involved heavily in the Cassini mission, which is what he's going to talk to us about today. He's going to talk to us about observations of the Titan Haze using Cassini and its instruments. So if you'll join me in welcoming Bob.
Cassini has been the love of my life for the last 20 years or so. The Cassini project started actually before 1990. I sent in a proposal to the imaging team in January of 1990, and my daughter was born 2 weeks later. And when she graduated from high school in 2008, that was the end of the nominal Cassini mission. And we have an extended Cassini mission that's going on now. And hopefully it'll keep going until 2017, when the plan is to crash into Saturn's atmosphere. But I'll be talking about some of the things we've learned up to this point on Titan's Haze. Titan is the only satellite moon in the solar system that has an atmosphere, and its atmosphere is actually much more substantial than the Earth's atmosphere. And it has a lot of interesting phenomenon, and I won't be able to talk about 90% of it just for the lack of time. I won't even be able to talk about a lot of the interesting new discoveries on the Haze. I'm going to focus on just a few things that I've been personally involved with because that's what I know about mostly. At the end of the talk, if I have time, I also have some slides on some of the results from the other instruments. So I'm going to start first giving a little background and history of Titan and the Cassini project. I'll spend a little bit of time talking about the physics, the principles of the remote sensing, how we learn about the nature of the Haze particles. I'll talk about some very specific observations, the descent imager and spectroradiometer on the Huygens probe, which went into the atmosphere in 2005, and also results published this year from the imaging science subsystem. And if I have time, I will cover some of the additional discoveries from some of the other instruments. These are some of the historically key points for Titan and Titan's Haze. Titan was discovered by Christian Huygens in 1655. In 1944, Gerard Kuiper discovered the methane gas, which was a strong indication that Titan has an atmosphere. In 1979, we had the Pioneer 11 flyby, which was the first chance we had to image Titan, spatially resolved images of Titan, and made some discoveries. In 1980 and 81, we had the Voyager flybys, Voyager 1 and 2. A lot more discoveries. In 2004, Cassini arrived, the orbiter plus probe arrived in the Saturn system, and in 2005, in January, the Huygens probe impacted Titan's atmosphere, floated down on a parachute over the course of about 2.5 hours, landed on the surface, and took images and gas chromatograph readings and several other experiments. Sent back a lot of information, and I'll be talking in detail about some of that information. The Cassini orbiter, which arrived in 2004, is still orbiting and still flying by Titan. We have close flybys of Titan on the average about once every couple of months. And we've had about 60 of them now, and we're going to go up to 90 or something like that. I forget what the number is going to be by the end of the mission, but we get very close to Titan during these flybys, and that's when we get most of our information. A little bit about the Cassini mission. The proposals were submitted in 1990, as I mentioned. The U.S. built the Cassini orbiter, which is a bus-sized spacecraft, a very large spacecraft for planetary work. And the European Space Agency built the Huygens probe, which went into Titan's atmosphere. Both were launched in 1997. The orbit insertion, both orbiter and probe together, was 2004. Several months later, the probe separated from the orbiter at about 90 days out from Titan impact and landed on Titan's surface in January of 2005. And we hope to go to 2017 with the orbiter. The Huygens mission only lasted about 3 hours, but in that amount of time collected a real unique set of data. And this is what Saturn and Titan look like with the orbiter in orbit around Saturn. Titan is that little thing on the lower left, but the solid body of Titan is actually larger than planet Mercury, so Titan is a planetary scale in its own right. Some basic properties of Titan's atmosphere. It's a very large satellite. It receives only about 1% of sunlight relative to what the Earth receives, so it gets very little energy, but what little energy it does get is important for driving the atmospheric dynamics. At the surface, the atmospheric pressure is 1.5 bar, which is about 1.5 times the surface pressure of the Earth. When you combine that with the low gravity on Titan's surface, which is only about 1/10 of the Earth gravity, that means the total amount of mass of atmosphere above the surface is very much larger than the mass of the Earth's atmosphere. So not only is Titan the only satellite with an atmosphere, it even has a much bigger atmosphere than the Earth's atmosphere. It has seasons. The seasonal period is about 30 years almost, and it has a slow rotation period which is synchronized with its orbital period, which is about 16 days. So it has one thing about the chemistry that I forgot to mention is that it has a mostly nitrogen atmosphere with trace amounts of methane around 2%, sometimes a little higher, and trace amounts of organic and nitrile particles, which eventually lead to the haze formation. And the haze is so thick that we can't see the surface until you get to infrared wavelengths around 1 micron or longer, and that's about twice visible wavelength of visible light. I'm going to say a little bit more about the rotation period and why these facts make Titan an interesting place to study for the atmospheric scientists, because it gives us a whole new example of an object that's very different from the Earth in many ways. And one of the ways is rotation. And so what I'm showing here are 2 panels. This is from a global circulation model from the National Center for Atmospheric Research that we imported to JPL and adapted to Titan. And one of the first experiments we did was to slow down the rotation of the Earth. Now, don't try this at home, but it has an interesting and initially perhaps unexpected result, which is, and you can't see it here because the contours are too dense, so I'll just point out, over on the right is the normal Earth that came out of this model, and on the left panel is the Earth slowed down to the Titan's period of 16 days for one rotation. And what's plotted here in different colors are contours of temperatures at the 500 millibar level for both cases. And for the Earth, it's warmest at near the equator, and it gets colder and colder as you get near the poles, as we all know. Now, when you slow down the Earth, those contours spread way out so that there's a huge region of the Earth that's pretty much at the same temperature all the way from north 60 or 70 degrees latitude to south 60 or 70 degrees latitude. That means that if we were able to slow down the Earth's rotation, I would start selling real estate in Antarctica because it would be as warm as Florida, and it'd be a nice place to live for a while. So why does this happen? I mean, this is not adding any greenhouse gas to the atmosphere. The only change here is slowing down the rotation of the Earth. And yet the high latitudes warm up tremendously. So I'll let you think about that for the next 40 minutes, and if anybody hasn't figured out the answer at the end, you can ask me. Moving on to Cassini now. These are some of the images from the Imaging Science Subsystem, which is ISS, and I'm a team member on that instrument, which we got early when we started getting close to Titan, and I'll just go through a few examples. This is what Titan looks like in real color. This brownish reddish stuff is the main haze of Titan, and if your eyes are good, you can see a very thin blue curve just outside of that, which is called the detached haze because it looks like it's detached. Actually, it's just a thin layer of haze that's separated from the main haze. And I'll be talking a lot more about that a little later. That was seen also in the Voyager images, and Kathy Rages, who is here in the audience, analyzed those Voyager images, and I'll be, again, getting into that in more detail. This is a little piece of the north polar region of Titan, which is in the winter hemisphere now, and you can see it has quite a few layers in it. So the north polar region has many other interesting attributes in terms of its organic chemistry, and it's called the polar vortex region. And again, that's one of the topics I won't be able to go into detail because I don't have time to cover everything. This is a close-up, on the lower left is a close-up of Titan's haze at a low latitude, like 12 degrees or so latitude, and we can see that even there, at very high resolution, this is a resolution of 250 meters per pixel, I think. Even there, you see this detached haze layer breaking up into many sublayers. Here we can count about a dozen or so sublayers in that detached haze. And then on the lower right is a contrast-enhanced image in a methane filter. Methane gas absorbs light, so in the methane filter we only see the highest haze in the atmosphere, and we can see that it has a pattern. It's tilted, so North Pole here, South Pole. In the lower left, there's an equatorial band, and you can, if you have good eyes, you can see banded structure at all the latitudes. So that's showing us that the flow is mainly in the east-west direction and very little flow in the north-south direction. So those are just some of the things we learned early on. So how is the haze, where does the haze come from? So we start with the recipe of nitrogen gas and methane is down 2% or so. Sunlight, ultraviolet sunlight, even though it's considerably less than at the Earth, still there's enough to break up the methane and the nitrogen into their constituent parts. There's ionization that occurs in the high atmosphere, and all those things together combine to form new chemistry, hydrocarbon chemistry and nitrile chemistry involving carbon, hydrogen, and nitrogens. Perhaps also not perhaps, but definitely, because we observed these aromatic rings, and the simplest one is benzene, which is 6 carbons and 6 hydrogens. And we believe that life gets more complicated from there on into things that are called polycyclic aromatic hydrocarbons, polyacetylenes, various nitrogen compounds, a lot of very interesting organic chemistry going on. So if you're in organic chemistry, this would be the perfect place to live, if you could live there. Anyway, eventually all that chemistry churning up high in the atmosphere, and this is happening about 1,000 kilometers above Titan's surface, which on the Earth would be way up there. I mean, a lot higher than any chemistry that we know of going on in the Earth. That combines to form particles, the Haze particles that we see. And in this slide, which is from a paper by Hunter Wade and colleagues, those particles are called tholins. And I believe we can thank Bishan Kari, who's here. I don't know if he's in the audience, but he originally, I believe, coined that name from laboratory experiments simulating the Titan aerosols back in the 1980s. How do we learn about the Haze properties, the optical properties, the physical properties? How big are the particles? What shapes are they, and so forth? So I'm going to talk about that a little bit now. These are some images and models from the imaging experiment. On the top row are images of Titan at different, what we call phase angles, which are labeled here. A low phase angle is where you're looking, where the sun is behind and you're looking at the full disk of Titan like a full moon. And a high phase angle is where you're looking at a high angle, and Titan is a crescent, and that's on the right-hand side. And so if you look at these, and these are all printed to the same brightness scale, you can see that Titan is relatively dark at the low phase angles and brightens up considerably at the high phase angles in the crescent phase. And that's a telltale sign that the particles in the haze are scattering light in the forward direction much more strongly than in the backward direction. And we know from physics, and I'll get into that a little bit more later, that means the particles are large compared to the wavelength of light. So that's one piece of information we've gained about the particles. Even though they're little tiny particles and we can't see them, we can get information on what their sizes are from these remote studies. In the middle row is a model, computer model, trying to simulate that, and it does a pretty good job. The ratio of the two is on the bottom. So this computer model, in order to fit the brightness at the different angles, we had to have a scattering function as a function of scattering angle that has a very strong forward peak near 0 degree scattering angle, has a very strong dip down to the middle angles, and then a little bit of a rise back in the back scattering angle. There's another piece of information we have that we can get from remote sensing, and that is polarization. And we got some of that from the Pioneer 11 flyby in 1979, and we got some from Voyager in 1980 and 81. And this is some work that I did with Peter Smith back in the Voyager days. These observations are the dots, and the curves are different models where we have different kinds of particles that we're trying to match up with the data. And you can see that one of the curves, the dashed one, matches up pretty well. And that comes from an aggregate type of particle, not a spherical particle, but an aggregate type of particle. But we first had to try models for spherical particles because those are the easiest ones to compute and to model. And 100 years ago, or 101 years ago now, a paper was published by Gustav Mie, who analyzed how light is scattered from spherical particles. He was the first one to figure out the equations. And you can check the math here, and if you find an error, just tell me. But the light is coming in, say, from the left, hits a particle, and then it's scattered in all directions. And he was able to mathematically treat that in a way that gave accurate results. And here's a picture of him. It looks like he's happy in that picture, and I imagine that was taken right after he discovered me theory, which is what describes the spherical scattering.
Question?
Yeah.
Is this composition independent? It's just the morphology of the particle, or is it connected in some way to its composition?
Are you asking about the me theory and the scattering, or?
Is the scattering that's observed dependent upon the composition of the particle, the atomic, the molecular composition of the particle, or is it just the morphology of the particle?
It's also the composition, because particles can be absorbing or not absorbing, and it makes a difference. They can have a high refractive index or a low refractive index, and that makes a difference. And for the spherical particles, me theory takes all of that into account in the equations. And these are some of the calculations that come out of the me theory, broken up into light that's scattered one time, light that's scattered two times, light that's scattered three times within the particle. These little diagrams on the right show the light traversing the particle and bending cause of refraction, reflecting off of the surface, and bending again and coming out, so forth. So there are ways to calculate all these things, and at the scattering angle 0 on the left, the first order of scattering and the total, actually the total of scattering is quite high, and that's what we see in Titan also, because this particle is larger than the wavelength. And then you get a lot of wiggles from interference effects, and when you have a size distribution of particles that are many different sizes, all those wiggles kind of average out, and you end up with the kind of scattering function I showed a couple slides earlier. So the spherical particles are able to reproduce one or the other of the two basic observations I mentioned. Either they can scatter light strongly in the forward direction, or they can be highly polarizing, but they can't be both, because the strong forward scattering requires large particles. The high polarization is pointing to small particles, and you can't do it with these spherical particles. So the conclusion is the particles on Titan are not spheres. So what are they? There were some laboratory simulations done in the around 1980 or so, and this is a published paper from the 1980s by Barnun and colleagues in Israel. And what they found in their laboratory simulations from acetylene, in this case, is that if you make acetylene cold in the laboratory, it forms these little spheres, but then they start to stick together and aggregate. And in the bottom panel here, I'm showing the aggregation, or one of the spherical aggregates of these things. So this gave me the idea to investigate the properties of these aggregate particles theoretically, and see if they could explain both the polarization and intensity. And I did that on a computer, and you can generate on a computer these types of things. On the left is a very fluffy aggregate, but it doesn't have to be that way. It could be more compact. And how do you calculate that now with electromagnetic theory? The way to do that is, one of the ways anyway, is to use a theory called, or a computer program, which does the discrete dipole approximation. So that breaks up any particle into a lot of small pieces, where each small piece interacts with the electromagnetic wave, and it oscillates like a dipole, just up and down. And you can combine all those little pieces together. In this example, all the little dipoles are combined into a spherical shape, and we can check this case against the me theory, which is for a spherical particle. So this is one of the examples that was done by Bruce Strain and his colleagues who wrote this code, this computer code. Using about 19,000 dipoles, he was able to get a very accurate simulation or reproduction of the scattering from a spherical particle. And since this theory, this method, does not depend on particle shape, we can use it for any particle shape. And that's what I did, along with Peter Smith. And we found that indeed these types of very loose aggregate particles can fit the high polarization and high forward scattering of what we found from Voyager and Pioneer and so forth. I'm going to move on now to the Huygens probe, which landed on January 14th, 2005. It was released from the orbiter 90 days or so prior to landing. It free floated through space, hit the atmosphere at a very high speed. It has a heat shield, which initially slowed it down to where it could deploy a parachute. And it came down on parachute about 2.5 hours through the atmosphere and landed on the surface. These are some of the instrumentation on the probe: gas chromatograph, imager, particle collector, meteorology experiment, several experiments. And the one I was involved with was called the DISR, Descent Imager Spectroradiometer. That was mounted on the edge of the probe so it could extend beyond the edge of the probe and look up and look down, take pictures and make measurements of the sunlight. So here is, if I can get this going, is an animation of what the DISR saw, only it didn't work. I don't know if I can do that. I don't know, it worked before, but in this setup it's not working. All right. Is it going? No? Oh, here it goes. So this was put together by Eric Karkoshke, who is also a member of the DISR team in Tucson. And it starts out looking at the sun for some reason, and I guess the Earth and the Moon were actually transiting about this time, because that's what's shown here. This is a view from a distant, when the probe was very distant from Titan, showing the Saturn system. And now the probe this is what it looks like from the probe's point of view as it's coming into Titan. And if you look on the lower right corner, it'll tell you what the phase is. Here it says free fall, and it'll tell you the distance from the surface in kilometers and the speed. So we can keep track of that as the probe is coming in. And here it's about to hit the atmosphere. So this is what it looked like from high in the atmosphere for the first hour or so. The surface is not visible because of the haze, but we're getting good observations of the haze during this time. And right now it's getting down to about 60 kilometers, and the surface is starting to appear. And it gets better and better as the probe gets down closer. And eventually you can start to see some dendritic channels, which are on a little bit to the right. This gray area is actually where the probe landed. Eventually it coming in down here, I think. And this little dot, which you may not be able to see, a little below the middle of the picture, shows the location directly below the probe, so you can follow that in as the probe comes down. Yeah, this is on the chute. The chute was deployed probably 120 kilometers, or actually higher than 100. The whole thing is on the chute, actually. Yeah. Here it's now getting very close to the surface, only 1 or 2 kilometers, down below 1 kilometer now at this point. And then it hits the surface, and now this is a rerun from a different angle. This one you can see those dendritic flow channels a little better. They're just below center, or near the center here. And that was clear evidence that liquid flowed on the surface of Titan, at least in the past. And the big question was, is it still flowing at these latitudes? It looks pretty dry at this moment. we didn't see any rainfall occurring. Methane, it would be liquid methane because the temperature at the surface is cold enough to liquefy methane. And it even gets colder as you go up in the atmosphere, at least for a while. So this broad area turns out to be very flat, and you'll see coming up some pictures from the surface. And if you look at the pebbles and the little rocks on the surface, some of them appear to be hollowed out and rounded with a little bit of hollowed out soil just beneath them, and that's an indication. And here's one you can see right in the middle now, an indication that there's been flow in this channel. The shadow of the parachute came overhead and was photographed by the camera, and that hot spot in the lower right is the surface lamp, which is also part of the DISR instrument, and it needed to have that because near the surface the sunlight is highly attenuated, especially at certain wavelengths. So they needed that lamp to sample the spectrum of the surface uncontaminated by the overlying atmosphere. And finally, a little picture of the sun as you would see it from the surface. And these are the credits. Again, this was mostly done or all done at the University of Arizona. Yeah. So I'm going to go into some technical details now of what the DISR study found. And I'm a little bit behind where I expected to be, so I'm going to rush through some of this stuff. There were many sub-instruments on the DISR. It had 3 cameras, 4 spectrometers, a solar Oriole camera, which was designed to look close to the sun to get that, sample that very low scattering angle part of the scattering of the particles. It had a UV photometer, and it had a surface lamp. It was a very complex instrument. The idea was to take pictures on the parachute and the probe was supposed to be spinning, and it was synchronized to the sun, so they had a sun sensor, and it was synchronized in such a way to make contiguous images as the probe rotated. Unfortunately, that didn't happen, and I'll explain later what happened. It had polarization measurements at 2 wavelengths. It measured wavelength dependence of the sunlight and the scattering from the Haze particles over visible and near-infrared wavelengths, both looking upward and downward, and measuring the surface reflectivity also. There were many problems. The probe spin was reversed relative to what it was planned to be, and I think it's still not known why that happened. It had spin vanes to control that, but they didn't work. And as a consequence, the whole timing of the sequence of taking images and spectra and other information from the DISR was thrown off, and data were taken in a more or less random fashion, and so that had all to be reconstructed, and it wasn't easy to reconstruct all of that because while this was happening, there was a lot of penduluming motion. The probe was at the end of a long tether from the parachute, and it was penduluming and rotating at different rates as it went down, and they had to reconstruct all this. And finally, there was a snafu with a telecom on one of the 2 channels, so half the data didn't get to the orbiter to be relayed to Earth. But in spite of that, as you could see from the movie, we did obtain a lot of very good data, and we can do a lot of good science with it. This is an example of how we modeled the atmosphere from the data. This is now the DISR Oriole camera looking back towards the sun. What's plotted here, the circular things are contours from a model calculation of the brightness, and it's brightest close to the sun, getting dimmer as you go further out. That irregular rectangle thing is the footprint of the DISR solar Oriole camera, which has a 6x50 subarray of pixels. And if you can see closely, if you look at this middle panel, there are little tiny contours within that rectangle, which are the measurements And we're trying to match those up with the model contours which encompass the whole thing. And that's going to require, in this case, 3,000 of these primary particles stuck together to form one aggregate particle. If you have too few, like 500 in the middle, or too many, like 10,000, doesn't work. So that's how we came up with a lot of information on the nature, the size of these particles. These are polarization measurements. The atmosphere is highly polarizing, and now we were able to measure the polarization inside the atmosphere as the probe went down. And at different wavelengths, different particle sizes give different results. And so we were able to constrain the primary particle size, the monomers, to have a radius of 0.05 microns. At that time, it's now revised to 0.04 microns from better calibration. So we have 3,000 of these small, tiny particles that stick together and form aggregates. These are profiles of the aerosol vertical distribution of particles. There's 3 regimes here. At an altitude of 80 kilometers and higher, the aerosols are following the gas density pretty well, so they're pretty well mixed. Between 80 and 30 kilometers, they form sort of constant with altitude distribution. So as you go down, the aerosol density is constant, and then at a slightly different value a little bit deeper in the atmosphere, but again constant. These are showing the wavelength dependence of the optical depth, which is again related to the particle properties, particle size and composition. And here we see 3 regimes. The one with the steepest curve here is the highest regime above 80 kilometers, and that's really these brownish haze particles we're seeing. Below that, there's a slightly less steep curve, and then even deeper below 30 kilometers, there's an even flatter curve. So that's an indication we're getting into a regime where there are some larger particles coming into play, maybe methane ice particles are in that region, and they could be larger. These are showing that what's called the single scattering albedo. It determines how bright or dark the particles are. If the value is 1, the particles are completely shiny, there's no absorption. And in fact, that's the case for some of the particles. The deeper ones get up to non-absorbing here at a wavelength of about 800 nanometers, and then they're absorbing at longer and shorter wavelengths. The higher particles are absorbing at all wavelengths, but they have a very similar shape, which indicates that the deeper particles are probably also have a high content of these brownish organic haze particles. And it's also telling us something about the composition, because this the dotted curve, which flattens out here at the longer wavelengths, that is from the laboratory work of Kari et al., and that does not show the absorption longward of 1 micron or so that's seen in the data. So that laboratory stuff is not exactly like what we're seeing on Titan. And these are a summary of the things that I talked about, so in the interest of time I won't go through that, but now I want to move on to a different topic, which is now from the orbiter. And this has to do with that detached haze and how it evolved over time. We went through an equinox period in August of 2009. This story really starts back in 1981 when Voyager 2 flew by. And this is an image that was analyzed by Kathy Rages and Jim Pollack from Voyager 2. They analyzed the detached haze properties, its altitude. These are a plot. This is a plot from their paper showing the altitude, and you can see at the equator on the left side the altitude is 357 kilometers. So when Cassini arrived, we also saw a detached haze, and these are some of our original measurements of it. It's that little bump. This is now brightness plotted on the vertical versus radius or altitude on the horizontal, and there's a little bump that's near 500 kilometers. So when we first saw it, it was around 500 kilometers, a lot higher than 357. So we were kind of scratching our heads about what's going on here. And then starting in the summer of last year, I started working with an undergraduate student, and his job was to try to run scattering models, computer models, to match the density of the haze layers that we're starting to see now. And the first result that he got was it didn't fit at all. The model had haze layers much higher than what the data were showing, and we thought something was really screwed up. And then we started measuring a lot of images. These are two of them, and you can see on the bottom scale, which are magnifications of the images on the top. Now with the altitude scale next to them, you can see that in 2010, the detached haze, which is that layer above the main haze, was now much lower in altitude than it was in 2006. And when we measured, and then we did some computer retrievals of the haze density, and we got these results for the two dates. The solid curve is 2006, and the dotted curve, or the dashed curve, is 2010. And this detached haze is a bump here at just over 500 kilometers in 2006. In 2010, we don't really see, it looks like it's more of a depletion rather than a bump. There's a big depletion, which makes it appear as a detached haze in 2006. So maybe it's a depletion of haze material that we should be paying more attention to rather than the bump. So we measured a lot of these images. Here's a plot showing 83 measurements from different times, and now we're plotting them relative to the equinox, which was August 11, 2009. And you can see the altitudes start out around 500 kilometers in the Cassini observations, and then as we go through equinox, there's a huge drop. And the Cassini measurements are those small symbols with error bars. There's a solid dot here, a big solid dot, which is the measurement from Hazes and Pollock from the previous equinox, or just after the previous equinox. And in the paper that was published earlier this year, we didn't have measurements that went out that far, but over the course of the summer, I made a couple more measurements, and one of them matches up in time relative to the equinox, essentially right on top of the Voyager time period. And the measurement essentially falls right on top of the Hazes and Pollock measurement. And I just think that's remarkable. This haze has undergone an altitude variation of about 150 kilometers over 30 years. And here we are 30 years later, and it matches up exactly within the error bars to where it was. So this is almost like an atomic clock in precision for a planetary object. I'm going to have to go through this quickly. There are a couple of models for the detached haze that we have in the literature. One by Ranu et al. is a model that combines dynamics with haze microphysics, and haze microphysics describes how haze forms, how it aggregates together, how the particles grow, how they sediment out of the atmosphere. And this, combined with the dynamical model, tells how they're carried around through the atmosphere. And in 2002, they published a paper which seemed to give a good explanation for the detached haze. Then in 2009, Lavas et al. Came out with a totally different kind of model that has no dynamics at all. The detached haze in their model is formed entirely by a haze microphysical process, and the idea there is that you have these very tiny monomers. The individual particles form high up in the atmosphere starting at 1,000 kilometers. They sediment down to a place where the density and temperatures are in the right conditions for these particles to stick together and form aggregates. So in their model, the detached haze layer is the signature of the aggregate formation process. And then once the particles grow in that layer, they get large and they fall out rapidly and through this clear space. So those are two different pictures. This is from the Ranu et al. Model, which is the dynamics coupled with the microphysics model. And you can see they reproduce the detached haze, although it's not in complete detail. The summer pole is on the left and the winter pole is on the right, and altitude is up. And there's a gap here near this summer pole. And that gap is not seen in the observations. In the observations, the particles are very continuous through the South Pole. So these observations of the detached haze are putting very strong constraints on how we think about Titan's. This is now in the high stratosphere. The amplitude of the altitude variations is very large, but yet over one seasonal cycle, which is a period of about 30 Earth years, the haze comes back to essentially exactly where it started 30 years ago. That's a strong constraint. Another one is that the haze is continuous or contiguous across the South Pole, which is the summer pole. And as I mentioned with the Ranu et al. Model, that doesn't happen because you have particles being advected from the deeper layers up to higher altitudes to form the detached haze, and where they're advected up to higher altitudes is in the southern high latitudes, and that's where the streamlines go vertical rather than horizontal. So that's a problem for that model. And another problem for that model is that the reason the detached haze drops in altitude in their model is that it's falling out of the sky. What's happening is the circulation is a big cell that goes from the south to the summer pole across horizontally to the northern pole and carries those aerosols across the planet in the detached haze layer in their model. Now, when the season changes and the heating reverses hemispheres, that model predicts, and you would expect naturally, that that circulation would stop, break up, and reform in the opposite sense when the heating is in the opposite hemisphere. And in the Ranu model, when the circulation stops, the particles fall out because they're no longer supported and they go away. But yet we're still seeing a very strong presence of the haze even today. And this was one of the most recent images we had. The last point in my graph was from this image, and it also shows Dione and Saturn. And I think I'm out of time, so I'll stop there. Thank you.
Bob, if I could start with the first question. So the height control of where the aggregates are falling out in the Lavas model, that is due to the difference in season and the heating of the atmosphere causing this process to happen at different altitudes. Is that?
Well, I didn't explain it because I was rushing, but in the Lavas et al. Model, it's a steady state model. And when they first submitted their paper, I was a reviewer, and it was clear that they thought that the Voyager observations at 357 kilometers altitude were not the same haze. They were trying to associate a higher layer, which was just barely seen in Voyager, with this layer that's seen strongly in Cassini. So their model is entirely steady state with no seasonal variations. It doesn't explain the seasonal variation at all. So it would have to be coupled with a dynamical model in order to account for the altitude variations that we see. It still may be a viable mechanism for the formation of the haze, but it would still have to be coupled with the dynamical model, and it isn't yet.
Since the atmosphere is primarily methane, it sounds like, what keeps replenishing it? Because as the sun breaks it down, you think hydrogen would escape into space or be captured by Saturn. What keeps replenishing the methane to keep the haze going up and down?
Yeah, you're absolutely right. At the current rate of destruction, I think the methane in the atmosphere would last 10 million years and then there wouldn't be any more. So there's three possibilities or two possibilities. One is it's not in steady state and it actually is being depleted and it won't be here in 10 million years. But this has been going on, for a long time, presumably, so that doesn't seem very likely. The other alternative, it's being replenished by probably subsurface reservoirs of liquid methane. It was originally thought that there would be perhaps an ocean of liquid methane and ethane because of this issue that you just mentioned. We see lakes on the surface right now, mostly in the North Polar region, but and those will last some time. But people are thinking there's probably a subsurface process, maybe episodic, rather than steady state. And then you have to start to think about models of the interior and how the interior evolves, and that's too far away from my field to comment on it intelligently.
Yeah.
Question.
Hi. In Los Angeles, the haze layer peaks around the evening rush hour.
And on Titan, it lasts 10 million years.
Yeah. It's a heck of a rush hour. My question is there any way to determine the average molecular weight of the material in these haze particles? And if so, does it vary seasonally?
There's been some work on that, but it's not easy. We have measurements from the INMS instrument, the ion neutral mass spectrometer on the orbiter, and also the particle analyzer instrument CAPS on the orbiter, and they sampled the high atmosphere as Titan, as Cassini flew through the atmosphere, and they see ions, negative ions that get up to of order 10,000 Daltons just at those high altitudes. So those are the precursors of the haze. So it's a hard issue to do that. We have one of the results I was going to show, if I had time, was measurements of solar occultation by the near-infrared spectrometer, VIMS, which shows a carbon-hydrogen bond, apparently haze material, carbon-hydrogen, not gaseous. And that was unanticipated by the Kari et al. Tholen experiment because it's not in those measurements. And they also saw, or they didn't see, some nitrogen-hydrogen bonds in their spectrum that they expected to see, which are in the Kari et al. Tholen measurements. So we're getting some information on that, and I didn't have time to talk about that.
You mentioned that benzene was one of the simpler organic compounds in the haze, and I was wondering if you had been able to take measurements or had a handle on more complicated organics.
It's difficult to get to that stage for two reasons. One is that the abundance of the more complicated molecules decreases relative to the simple ones, and so you have to have a very sensitive instrument, more sensitive than the INMS or the neutral mass spectrometer that sample the atmosphere. So the instruments that we have just aren't sensitive enough, and the more complicated ones are also hard to determine spectroscopically, pretty much for the same reason. So we don't have that.
Yes, when the probe is zooming by Titan and you're doing these altitude measurements, how do you get your base reference? Radar?
There was a radar reference that was active through part of the descent. And there was also a Doppler measurement. And how that was done in detail, how that was all put together in detail, I'm not sure. I think they relied on a certain part of the atmosphere where the surface was observed by the camera. They could measure the size of features as the surface was observed as the probe went down, and bootstrap that into the cycle also. So they used all those things to do that.
Well, was the defense or the descent pathway, did that give you any information on the winds and circulation?
Yes, there was information, and we have, there was observed a layer of strong winds, and I forget what altitude that was observed, but it was totally unexpected. And aside from that, the more general properties of the wind field were observed from the Doppler tracking, which was done from Earth, actually, because they had a Cassini, the Huygens Doppler experiment, which was supposed to relay to the orbiter, I believe, and that was all over telecom channel B, which was lost. So that entire experiment was lost, and that was the biggest loss that we had because of the telecom problem. But nevertheless, we did get Doppler from ground-based observing. And that was another remarkable aspect of the mission.
And second question has to do with the evolution of the moon. How, any ideas about how it formed and how it's evolved over time?
People have ideas. I don't think I'm qualified to comment on that, because I'd start saying something and it would just be too superficial, I think, to be able to make good sense. But people have talked about warming early on in Titan's history and warming at various times later in the history, and they try to account for the atmosphere as it is now and as it may have been, and the fact that methane is being destroyed with a lifetime of 10 million years. I know that the presence or not of liquid ammonia is very important, because the melting temperature of liquid ammonia plus water solution is lowered when you have liquid ammonia. You have to try to account for the nitrogen gas in the atmosphere, which is the main component. 98% or so is nitrogen. So if that came from ammonia, or was it acquired from the original primordial nebula? And so those are the questions people are addressing with their models, and I'm sorry I can't give you any real insight into that.
A much easier one. Why did the probe stop transmitting?
The plan was for the probe to transmit for about 3 hours, because the telecom was from the probe to the orbiter, and the orbiter was phased in such a way so that it could see the probe during the descent and for about a half hour on the surface. And after that half hour, the orbiter just kept on going and was out of sight. There was no line of sight between the orbiter and the probe after that period. And so the orbiter went on its way, and the next time that you got close to Titan was a month or so later, and by that time the probe was no longer functioning.
Is the polar hood that you mentioned that might show up in the north region like the hole in our ozone layer? And is there like global warming, as it were, on this moon as well, like on Earth?
The first question, I'd say, yes, it's like our own polar vortex, in the sense that a polar vortex is a unique meteorological environment. In our case, ozone has a chance to build up in the polar vortex region, which is in winter. Both of these are in winter, both Titan and the Earth. And in the case of Titan, we see interesting chemistry in the polar vortex region, organic chemistry, and some things condensing in the polar vortex region, which we do not see in the rest of the planet. The detached haze, which I mentioned, does not continue into the polar vortex region, and there's a whole host of phenomena. So the polar vortex is meteorologically essentially a boundary, at least on Earth, or it's hard to cross that boundary in the stratosphere. So you have a whole special set of meteorological conditions in the polar vortex.
Okay, you keep mentioning 10 million years as a lifetime for the methane. Is that a half-life or 10 half-lives, or what is it?
Essentially, all the methane would be depleted after 10 million years
So
at the current rate of destruction,
it's like 10 lifetimes or something.
I guess.
Half-lives.
Last question.
Can you answer your puzzle from the beginning of the talk about how the rotation speed of the satellite would affect the temperature profile?
Yeah, good question. So what I showed earlier was that the temperature contours, when you slow down the Earth, the temperature contours spread way out, and you get temperatures near the poles that are essentially no different than they are near the equator. And why that happens is that when the Earth is rotating once a day, as we are familiar with, there's a strong Coriolis force. And if you know what that is, it's a force due to the rotation. And when you slow down the Earth, that force diminishes greatly. And that force has the effect of diverting air that would normally try to equalize the temperature. So warm air near the equator would normally try to flow to the poles, because otherwise there's a strong temperature gradient set up. The poles would normally like to be cold, and this equator would like to be warm. And an atmosphere is very good at trying to neutralize that tension. And it would normally try to set up the flow between the equator and the pole. but it's thwarted by the Coriolis force, which diverts the flow into the east and west directions and sets up these high and low pressure cells. And instead of getting efficient flow towards the pole, we get very inefficient flow, and that can maintain a strong temperature difference between equator and pole that you can't maintain for a slowly rotating body like Titan or Venus.
Okay, with that, we have a special antique SETI mug in commemoration of your talk, Bob.
Thank you.
And please join me in thanking Bob for his great talk.